Good morning and welcome to the latest in the Fire Safety Matters webinar series. Delighted to be doing this in partnership with FFE today. Our presenter is Nigel Ward, and really delighted that you guys could join us today. Couple of bits of housekeeping, if you don't mind. As you know, we now offer a CPD hour for this. Now, many of you are going to be asking, how do I get to that CPD certificate? Don't worry, I will email it to you this afternoon when I send you the on-demand link. So that's the second point. This webinar will be available on demand from this afternoon. Please do share it with your colleagues. They just have to register for free like you did. You can watch it on demand as often as you like. Many of you will ask me, can we get a copy of the slides? The answer is the only way you can see the slides is by watching the webinar on demand. And as you know, the topic today, we're going to really be covering protecting large premises from fire via optical beam detectors. So we will do a write-up on the website of this as well. But the most important thing that I can ask you all to do is to please submit any questions you want via the questions box at the bottom. If you're having any technical issues with sound, slides, anything like that, there's a little robot icon in there. Use that for any technical help. Don't use the questions box. But please do get your questions in. Nigel will take questions as soon as his presentation is over. So other thing to remind you is Fire Safety Matters. We've got all the latest news from FFE and the whole fire safety sector through our website, which is www.fsmatters.com. And we also have a fortnightly podcast, and FFE will be on, I think, episode 4 or 5. We've done 3 so far. So it's free to download through iTunes, Google Play, Spotify, or YouTube. Just type Fire Safety Matters podcast. Anyway, that's the housekeeping. Very much looking forward to coming back in to do the questions with Nigel. But Nigel is the main event today, not me. So good morning, Nigel. How are you?
Good morning, Mark. Good morning, everyone. So this morning I will be talking about optical beam smoke detections, and as Mark has said, if you've got any questions, then please submit them, and I will answer them as fully as I can. So, FFE are currently the biggest beam manufacturer in the world. We've been in business since 1974. We make primarily beams, but also optical beam, flame detectors and vibration switches, and also we have a little line in aviation fire extinguishers. So, global news. The Notre Dame Cathedral was badly damaged by fire back in 2019, although it seems quite a long time ago now. But the main thing that came out of this, the investigation, was the fact that only the common areas of the cathedral were protected. There was no protection in the roof space. And as the contractors were working up there, that was a bit of a combination for a disaster, as it turned out. So what is important to do in any building is have some form of protection, and hopefully, from our point of view, optical beams up in the roof area to protect against any alarms. So this is what I'll be going through. It's mainly concentrated on our latest beam, which is the Fire A1. That has got a lot of sophisticated features in there, as we'll see. What we're going to cover is how, what and why. So basically, why would you use a beam and what it is, versus different types of technology, the features of the Fire A1, how you would install them, the line of sight, and the sort of applications that they would be installed in. So the definition of a beam detector is quite convoluted, but it's an optical beam smoke detector uses infrared, which is transmitted and received to monitor an open area. So in a nutshell, what that means is it transmits an infrared signal, and the detector is expecting to receive the same signal back. If it is lower, or it can be higher, but normally it's lower, then there's a problem. So when it transmits a signal, however it does it, whether it's an end-to-end beam or a reflective beam, it's expecting the same signal back. Here's a slide which shows comparison to sort of detection that you may find in an office or a small building. The thing to note with this is that the beam detectors can work up to 25 metres in the standard configuration, but they can go up to 40 metres if you have the right scenario, which is generally you need supplementary detection, or the beam needs to be in the top 600 mil of the roof space. So where would you use a beam, and why would you use a beam? The vast majority of our beams are used in warehouses, distribution centres, but they can be used in areas where you have restricted access. Also, explosive environments. We have an ATEX rated beam. They're very discreet, so unlike maybe point detection or aspirating, you don't have to put the beams in the middle of the ceiling of a room or the risk area. They'll always be on the walls, typically, and so they can be hidden and be more discreet than other forms of detection. They are cost effective to install because, again, you only really need to get up to the walls of a building. Once you're up there, then hopefully that will be the last time that you need to get back up to a beam. So, how do they work? There's two types of beam detector. Historically, the end-to-end one, transmitter and receiver, was the first type. So that one transmits an infrared signal from one end of the building and is received by the receiver at the other end of the building. The advantage of this beam, the main advantage of this beam, is that it has a fairly narrow line of sight, which is something I'll come back to later on. This beam typically can work through 600 mil to 300 mil of space. So if you've got a gap of 600 mil in a roof area, or down to 300 if you've got the right conditions, then that's the beam to use. The downside of that beam is that you need power at each end and it's manually aligned. The reflective type, of which the vast majority of our beams are reflective types, are easier to install. You only need power at one end of the building. The signal is transmitted down to a reflector, or as a prism as it says on the screen, and is bounced back and is analysed. The main consideration for this beam is that you need a metre of clear space to align the beam through. The reason for that is the signal is going down to the reflector and coming back. So if it hits any obstruction on the way down there, and that typically would be girders or ducting, or even if you've got glass down where the reflector is, then you need to take that into account. And if you can see from those slides, the infrared is like an ice cream cone, a traffic cone. It gets wider the further it goes. So the longer the beam's distance it's covering, the more important it is to get the meter clearance for the end-to-end beam. So how do they work? The reason we use infrared is for two reasons. First one, probably the most obvious, is invisible, so it's discrete. For your information, it's just on the near invisible spectrum, so it's only just invisible to the naked eye. But the other reason, the important reason, is that it's obscured by smoke, and anything that enters the beam's path, as you can see from this little slide, will reduce the signal, and when it reduces the signal to a predetermined level, then we'll get an activation or a fire, as it would probably be more commonly known. So very different types of technology can be used as well as beams, but here's a scenario where if you had a room which was 30 metres by 120, I know it says 52 detectors up on the screen, but you would need 48 point detectors to cover that same area. So it's giving the idea that in a scenario where you could use beams or point detectors, you would only need 2 beams versus 48 point detectors to cover an area of 30 metres by 120 metres, assuming that you could fit, you could fit them all in their optimum positions. The more common form of comparison technology, though, competitive technology, is aspirating smoke detectors. Aspirating smoke detectors are can be very sensitive in comparison to beams, but they do have a slower detection time over longer distances. The reason for that is that the smoke if the smoke enters the last sampling hole, it can take up to 2 minutes to travel. That's under the British standard. It can take up to 2 minutes from entering the hole to giving a response at the detector, whereas at a beam doesn't lose sensitivity whether you're at the furthest end of the beam or closest end of the beam. So that's an interesting factor to take away there. Aspirators are expensive to install, and you can have issues with pipes getting clogged up, and potentially different pressures can cause poor responses on the flow of the airflow. But that's really the best sort of comparison technology between a beam would be an aspirating smoke detector. So, far-array 1. The far-array 1 is a reflective beam, and it's our most recent beam. It was released about 18 months ago. There's 4 highlighted points on the right-hand side of the screen, which I draw your attention to. Historically, if I start from the top left, historically, beams have always suffered from problems of direct sunlight. So what light cancellation technology does is it compensates out strong infrared sources, or most typically the sun, from causing a problem on the beams. I was doing some work from home a few weeks ago, and I had a beam set up in direct sunlight, a far-array 1, and I couldn't get it to fail, which I was really impressed about, even though I was trying to align the beam into the sun. Older beams would definitely have false alarmed in that scenario, or they wouldn't have aligned. We have an inbuilt laser and an auto alignment feature on the far-array 1, so it's for a self-contained beam, it is a lot easier to use than the beams that went before it. Other features that are worth considering or worth noting is something that we're calling dynamic phasing. Again, in the past, beams have been fairly crude in the way they transmitted their infrared. It was basically a square wave of just a square pulse train of on-off transmission of infrared. But because of that, if you had beams pointing at each other, you ideally needed a big board, say 1 metre square, to put the reflectors on to block off infrared passing from one side to the other. Obviously, in some buildings, that doesn't look great. In warehouses, maybe not a problem, but in some buildings, it's not aesthetically pleasing. So on the far-array 1 and all the future generation beams that we're releasing, the beam transmits on a random frequency, which is selected at power up. So the chances of 2 beams interfering with each other is pretty remote, or if not impossible. They also have a more sophisticated building tracking movement. One of the problems people used to comment on beams in the past is they go out of alignment because the building's expanding and contracting. So our far-array 1 will compensate for small amounts of building movement that can occur during the day. So now we have a little video.
And just before we go into that, just a quick reminder to everyone before we play the video. Obviously, we're going to go silent so you can hear the video. I think it's about 6 minutes in length, isn't it? I think, Nigel.
That's correct, yeah.
But this is the perfect time for you to use the questions box at the bottom. We've had a number of you send questions in. Please keep them coming. Nigel's here for you guys, so please do send in the questions. So yeah, Nigel, if you just click to the next slide, the video will play when you're ready.
Here we go.
Hello and welcome to our far-array 1 setup guide. The far-array 1 was designed from the very outset to be easy to install and commission for reliable use of smoke detection in large open areas, and can be used with both conventional and addressable installations. So, if you're ready, let's make a start. First thing, let's have a look at everything we have in the box, and this is what you should have. A user guide, a FireRay1 base, a FireRay1 detector head, a short-range mask, and a reflector. Installation of FireRay1. To get the best performance, let's look at a few tips on how to install it correctly. They are: 1. Make sure the device is always mounted onto a solid surface. 2. Never position the unit so that any objects can break the beam's line of sight. 3. Always keep a clear area of 0.5 meters around the unit. 4. And lastly, always try to position the unit as high as possible, while still ensuring you keep more than 0.5 meters from the top of any ceilings. Remember, all installations should comply with local regulations, and when you can meet all of that criteria, you can then fix the base unit onto the wall. Connecting the unit. Power. The unit itself requires a low voltage supply, which should be connected here and here. This voltage needs to be between 14 volts and 36 volts DC. FireRay to panel. Now connect the FireRay1 to the fire panel. These connections are here and here. Resistors. You'll notice the alarm resistor for the unit is wired across these terminals, here, and the end-of-line device, here. You must always ensure these components are the correct size and rating for your fire panel. Now, some fire panels don't require an alarm resistor, but will require a short between the two terminals here. Checks. So, once our unit is fitted and the connections are made, it's time to check a few things before we move on. There are several setting switches that are preset at the factory, but under some circumstances may become altered during transit. Therefore, it's important to always take a moment to ensure that these are set up exactly as laid out here. As previously mentioned, check that your region's regulations require a resistor or a shorting wire. 3. As previously mentioned, it's important when fitting any detector that you always use the correct resistors as recommended by the manufacturer of your fire panel. Failure to do this may cause the unit to malfunction, so it's always a good idea to double check. So, once all of those items have been checked, we can fix the detector head onto the base unit. Make sure to plug the cable from the detector head into the connector on the base. Now, simply push and rotate the detector head clockwise until it locks into place. Fitting of the reflector. The next job is now to fit the reflector, ensuring it is directly opposite the unit and once again fitted onto a solid surface. It's important to point out that the FireRay1 can use different combinations of reflectors dependent on the distance you want to be protected. Our top tip here is that the unit is only supplied with one reflector, so if you're going to be fitting the FireRay1 over distances longer than 50 meters, you'll need to order extra reflectors. So, now we have everything fixed, wired and ready, it's time to set the unit up, and it couldn't be easier. To turn the laser on, move the slide switch to the left. After a few seconds, you'll notice a red laser appear on the opposite wall. Use the direction keys on the base to move the laser point onto the reflector. It's not critical that the laser must be in the very middle, but it should be close. Once you're happy that you've targeted the FireRay1 correctly, simply move the slide switch to the right and wait for the unit to automatically align. You'll know when it's done when you hear the unit make a small click, and the green light will flash for 10 seconds. This should take no more than a minute. The green light on the underside of the reflector will now flash green once every 10 seconds to show that the system is operational. And when that's finished, simply fix the door of the base back on and you're ready to go. To check that the fire array 1 operates and alarms in a fault and fire condition, we need to carry out a couple of simple tests, which are to simulate a fire condition over 3/4 of the reflector with a non-reflective material and wait for the indicator light on the bottom of the unit to flash red. To simulate a fault condition, cover over the full reflector and wait for the indicator light on the bottom of the unit to flash amber. When the tests have been carried out, the fire array 1 will reset and the indicator light on the bottom of the unit will flash green. The fire panel should show fire and fault when the fire array 1 is being tested for these conditions. And that's about it. It really couldn't be easier. We hope that you've enjoyed watching this quick setup guide, and thank you for choosing FFE for your detection requirements.
Okay, so I hope that played for okay for everyone. So we're looking at the user controls. I know this was covered a little bit in the video. We've got on the fire array 1, we've got a slider switch which controls the alignment side of things. 3 little indicator LEDs which lets the engineer operating the device know what the alignment state is. 4 little push buttons which guide the laser onto the target, and then we've got an 8-way dip switch where you can select the sensitivity, the latching alarms, and the type of alignment mode that you would like to operate or like to use it in. Now we've got another little video. It's only a minute long, this one, and that just describes how the beam aligns.
Well, that video temporarily stopped working, so I think we'll just move straight back onto the next slide, Nigel, if that's all right.
All right. Yeah, because it seemed to freeze on my screen. Okay, everyone. The install requirements for beams. This would be generic across all the types. Doesn't matter whether they're reflective or end-to-end versions. But say we're using the fire array 1 as an example here. So this shows the distance that you need for the reflectors. So the 3 reflector ranges are from 5 to 20 meters, 20 to 50, and from 50 to 120 meters. Now note the cone that's coming out of the detector. If you remember before, I said that you need a 1 meter, ideally a 1 meter diameter the whole of the way down the beam's run. The longer you go, the more important that is, because as we can see here, the infrared is getting wider and wider. And if you look at the little image inserted in the bottom, we can see that there's some roof obstructions. So those ones, the further you go, the more important it is to get the clearance from them. Just going back to the number of reflectors, you only need 1 reflector up to 50 meters for a fire array 1, but if you're using it at less than 20, then we provide what we call a short range mask, which basically reduces the size of the reflector area, and it makes it easier for the beam to actually align onto. If you go above 50 meters, you do actually need 4 reflectors, and so anything from 50 to 120 meters, you will need an extra amount of reflectors. So the other question that commonly gets asked is the actual width that the beams can cover. If we assume that a roof was flat, then you have on all beams you have a maximum of 7.5 meters on either side of them. But if you have a pitch group, as we see here, then you can extend the coverage of the side-to-side coverage of the beam that's in the apex. So the beams that are on either side of the apex, you can't expand their distance, but you can on the one in the middle. So if you know the angle of the roof and you can work that out through basic trigonometry, you can add up to 1% of coverage for every degree of angle up to a maximum of 25 degrees. So if I go to the next slide, we see that if we have an angle of 10 degrees, we can increase the side-to-side coverage of the apex beam to up to 8.5 metres. And as I said, the maximum that you can get is 25 metres, and that equates to a total width of 18.75 metres for a 25 degree or more angle. Fixing beams is very easy. They typically just have two mounting holes, which are an M6 or a 4.5 diameter, 4.5 inch, I'll get it right, quarter of an inch diameter screw will be able to mount them onto the wall. The angle of misalignment. With reflectors are made out of the same material as road signs. So basically, whatever angle the infrared hits the reflector, up to 5 degrees, it will bounce it back. So we do make a wide variety of optional extras which allow you to angle the beams. But if the surface that the reflector is mounted to is not 100% flat, excuse me, or not 100%, if it's an older building, maybe the wall isn't particularly smooth, that's not a worry. As I said, so anything up to plus or minus 5.5 degrees offset on a reflector is not going to affect the actual beam's performance. This video shows some guys aligning the beam. It's just them seeing if they could fit a beam through a small gap. I wouldn't advise you do this in real life, but it's just something that they were trying to do. This is about a minute.
Un poco más. No se muevan, ¿eh? Un palmo, menos un palmo. Not even 15, no, 20 centimeters away from the beam distance. A ver, un poco más, cierra un poco más. Un poco más. Ya están, pero hasta ahora. Un poco raro. Abrimos un poco ahora.
That's not something I would advise you doing in real life. It was just something that they wanted to see if the beam was set up for a small gap like that. But over longer ranges, that wouldn't have succeeded. But notice in the background of this, we've got sunlight coming through, and that's something I'll come back to in a slightly later slide. So, common applications. The thing to take away from these slides is that they're all big spaces. I would say the vast majority of our beams are installed in pictures like the bottom left, so warehouses, distribution centres. But anything where you've got a big open space that you need ease of protection and ease of maintenance, then the beam is a good choice to go for. If you look in at the bottom right photo, anything where you've got a lot of glass in, you need to take that into account when you're choosing a beam. Unless the reflector is in an area where you've got at least, say, 0.5 metre from the reflector to the nearest glass surface, then I would always recommend that you use end-to-end beams instead, purely because the signal's going in one direction. So any bounce back from the glass doesn't actually affect the beams themselves. But a reflective beam, if you get bounce back from another surface, then the beam doesn't know where it's trying to align onto. So with atriums, and if you've got a lot of glass, think about whether a reflective beam is actually suitable for that particular application. Accessory ranges, we make a wide variety of accessories which help installations. The most important one of the ones we see here are the anti-condensation heaters. Historically, beams have always had issues with condensation in the winter months. So basically, if you've got an unheated warehouse and the temperature is dropping to sort of like below dew point, then we can get a build-up of moisture on the detector and the reflector end if it's a reflective type, and that will cause potentially a false alarm. And the trouble for a service engineer when they come along is the fact that if the moisture is evaporated, then the engineer won't know what caused the problem. But if you're fitting beams in areas where you're expecting maybe condensation could occur, or it's in maybe a chill store, it's worth thinking about fitting the anti-condensation heaters. And I said I've got experience of using those, and they do work really well. But like I said, it's something you need to think about when you're choosing a beam. Maintenance and testing. There's a lot of things on here. The most important thing would be to look at the beam's compensation value, the AGC value, if you can find that. That is only on beams with controllers, but that will tell you whether the signal has been going up or down on the beam. If you've got a big change, it starts off at 0 and the beam can compensate up and down if the signal has been increasing or decreasing. If you've got a big change in signal, then that might indicate that there's something wrong with the beam. Either something's moving, as in it might not be on a solid surface, or maybe there's a lot of airborne contamination. So you can use that for I think the word of it, sort of like maintenance where you preemptive maintenance. That's the word I was looking for. Preemptive servicing. And the third thing at the bottom, you should always test the beam for fire and fault at the actual beam itself. The beams that have got controllers on do allow you to do testing from the controllers, but I would never recommend you do that. That's purely for proving the relays are working, and during the commissioning stage, it saves the engineer having to keep blocking the beam. But for a service visit, you should always block a beam to get a response. If you don't do that, then you can't say 100% sure the beam is working. Also, you should always test, a bit like with an aspirator, you should always test the furthest point of the beam. So if it was an end-to-end beam, you would test the transmitter end, and if it was a reflective beam, you would test the reflector end. So, golden rules. And this is the penultimate slide now, you'll be probably pleased to know. So, the first thing, the most important thing, if you're choosing a beam, what I would say is a beam suitable for the site? So, as a rough rule of thumb, if your eye can see something, the beam can see it too. So, if you've got a lot of airborne contamination or a lot of dust, anything that's up at high level where the beam is likely to be installed, then a beam probably wouldn't be a good choice for that. I've been to a paper shredding factory which had beams in, not our beams, but it would have been the same regardless. And there was a constant cloud of dust up in the roof area, and the beams were always in fire or fault. So the customer had switched them off, and basically it meant they had no protection. So that would be the first thing, make sure a beam is suitable. When you're actually installing them, you need to install them on a solid wall. The more solid, the better. If you remember back to an earlier slide, we said that we can move the reflector end about, and that would also go for a transmitter as well. So if you've got two walls, like the building I'm in at the moment, I've got a brick wall on one end and a plasterboard wall on the other end. then you always put the detector on the solid wall and the reflector on the not so solid wall if you have a choice. But ideally, you want them to be as solid a structure as possible. We need a good clearance around the beam. So ideally, for an end-to-end one, we need between 300 and 600 mil, depending on the application. But for a reflective type, we always recommend the metre diameter clearance. And also, we don't want anything coming into that space. So a typical issue may be in a warehouse where you've got a forklift truck putting pallets on top of racks, and the beam might be going across the rack, or it may be down in the alley where or the space where the forklift moves up and down. I've seen this quite a few times where the forklift will break the beam and then put the pallet on the rack. So as long as it can do it quickly, it's not normally a problem. But that is something that is a common cause of false alarms or faults on a beam. Airflow is something that people may not take into a consideration. But if you've got something where you've got a lot of extractor fans, for example, or something where the air can move around, it might prevent any smoke that you've got rising up to the roof area quickly, and then that would result in a slow detection speed. So it's something that people don't really think about, and I appreciate it's hard to take a lot of these things into consideration. But if you did have a big warehouse with extractors in for some reason, then maybe again beams probably wouldn't be a good choice in that particular area. And then, as I've discussed earlier, sunlight and strong infrared sources can be problems. Sodium lamps affected the older beams that we made because they give out infrared. But on the new range of beams, because they're a lot more sophisticated, they are practically immune to just about every infrared source because of the way they transmit and receive. If you remember, I said that the older beams transmit on a sort of like a pulse train. On the new beams, they are pulsed randomly. So it's a continuous random pulse. So that way, it's unlikely that an artificial source could be generating something that's similar. So just to sum up then, you need, if you're using a beam, try and follow the golden rules. And now we're at the end, so I'm open to any questions, Mark.
Brilliant, Nigel. Thank you for that great presentation, as always. We've had a number of questions in, but this is your chance. We've got, up to about 15, 20 minutes of questions if we need them. Keep them coming in the questions box at the bottom. Don't be shy. Please do submit the questions. For those of you that have asked a question, as I said before, how do you get your CPD hour for this? I will email you your CPD certificate. It doesn't have names on it, but it's given to the institution of fire safety managers. I will email that direct to you. You'll also be able to watch this on demand. The email will have the link to on demand. But in all honesty, if you came in via the same link this afternoon, you'd be able to watch it on demand. And that's the only way you can see Nigel's slides again, is through there. So, Nigel, I'm going to fire away while we get more questions coming in, I hope. First question for you comes from Tony Shepherd of City University. What are the costs per unit, and can they be installed in a house?
That's a good question. I wouldn't recommend you install them in the sort of house I live in. Basically, because the roof would be too low, or the ceiling would be too low, I should say. So you could put them potentially on a staircase, for example, but the cost of them would be a lot more than a basic point detector, that's the sort of thing you might have in your kitchen or on your landing. So unless you've got a big, say, stately home stroke manor house, I think you'd find that beams would be prohibitively expensive in comparison to a point detector. But the other thing is, even if they were a similar price, if you put anything in front of a beam, then it will react. So just say you were vacuuming, or dusting or something, or you're doing some changing a light bulb. If you get in front of the beam, then it will react. So that is why they're typically not used in offices or regular houses.
Okay, and just a follow-up question. I don't know if you're happy to answer it, but he did ask what the cost of unit was. I'm not sure if you covered
Right.
that then.
Yeah, sorry. I'm not in sales well, I used to be in sales admin. The typical cost of a Fire A1 is about £200, but they vary. If you're a customer who buys a lot of them, then you'll probably get them a little bit cheaper. And if you're buying them at cost, it may be 250, but they're a lot more expensive than sort of point detectors. So from that perspective, they would never really be used in a house unless it was maybe, like I say, a stately home or a manor house. Or, for example, you know, I don't know if any of our directors have got them in their houses, for example, just to show them off, but I certainly haven't.
So Tony's actually clarified. He's come back to us. He meant, sorry, I meant, can they be installed by in-house engineers?
Oh, sorry. Yes, of course. Yeah, they're very simple to install. Basically, you just need a 24-volt power supply and then a connection back to your fire panel. So I've dealt with sites. For example, I went to a cotton mill a few years ago, and that was with our flame detectors. But you'll get my drift on here. They had an on-site electrician, and we had a meeting with the guy, and they called the electrician in, and we showed it to him, and they said, "Can you install this?" He goes, "Yeah, no problem." It's literally just wiring back to the fire panel. In theory, you would need someone to inspect it to make sure it's been done properly. That would be the only thing if you've got in-house people doing it. It's purely for your own peace of mind that they've actually been tested properly. So I'm sure anyone could wire in a beam, but it's whether the tests have been done to the fire panel and you're happy and the user is happy that they're working correctly.
Okay, so another question that's come in a couple of times. Does the sun affect beam detectors?
Yes, it does. I covered this a little bit on the presentation, but the older beam detectors will definitely go into fire if the sun can shine directly onto them. The Fire A1, because it's a new generation of beams, that's got technology which is resistant to sun. We call that light cancellation technology, and it's also resistant to strong infrared sources such as old-fashioned sodium lamps. To recap on something I said earlier, I set a Fire A1 up in my garden a few days ago when it was very sunny, and the beam set up fine. I wouldn't have been able to do that with the beam that it replaced or any of our other current beams, because they just don't have the technology to cope with sunlight. What happens is the sunlight swamps the infrared frequency that they're looking at, and then the signal just collapses, and it will typically go into fire before it goes into full. So in the spring and the autumn, you may find if you've got sun shining through windows, they can shine onto beams, for example, in atriums and cause problems. If anyone wants to submit some sort of questions offline by yourself, Mark, I'm quite happy to send photos and stuff of to show you know, that these sort of applications and what is not a good idea to do.
Okay, no, brilliant. Thank you for that, Nigel. Another question that's come in a couple of times. What's the maximum height you can use a beam detector at? Right,
the standard height in the UK, all these are based on the UK, because in other parts of the world the regulations are slightly different. But in the UK, the standard height is 25 metres for a beam. You can go up to 40 metres, but there's two caveats you've got to meet on that. The first one is that if you're going to use a beam of up to 40 metres, it must be within the top 600 mil of the roof. If you can't achieve that because you've got obstructions or, you know, various things that you're trying to miss to get the line of sight from one end of the building to the other, you need what we call supplementary detection, and that would be beams mounted at a lower level. So when you're mounting them at a lower level, just say they're mounted at 20 metres, you would mount the beams a lot closer than what you would do normally. So if they're supplementary detection beams, If you've got them mounted at 20 metres high, then the distance between them is a quarter of whatever the height is. So if you've got a building that was 40 metres high, you've got a beam in the roof, and you've got a supplementary level at 20 metres high, you could space those beams at every 5 metres across the risk area. The thing is, I've never seen that used in the UK. There's only one application I can think of, and that was in a hotel in New York, where they had like a glass atrium up the side of the building where the lifts went up and down, and they had beams at every floor. But in warehouses, you would never be able to use a beam with supplementary detection because you'd have obstructions in the way. So in reality, 25 metres is the practical maximum height that you could use a beam at.
Okay, before I ask an obvious follow-up question to that, just we are getting a steady stream of questions coming in, but do keep using the questions box at the bottom of your screen to get your questions in. If you don't mind me asking a question, I know I'm kind of abusing my power here, Nigel, but what's the actual maximum width a beam detection can cover? Right.
The maximum width, standard width, and this goes for every type of beam, whoever makes it, is 15 metres. But if you've got an apex roof, so if you've got like a triangular shaped roof, if you know the angle of the roof, and you can work that out through basic trigonometry, if you can remember Pythagoras theory, you can work out the angle of the roof. Up to 25 degrees, you can add 1% of coverage for every degree of angle. So there was a slide on that where we said that if you had an angle of 10 degrees, you could increase the side-to-side coverage from 7.5 to 8.25 metres, giving you 16.5 metres in total. So it's only for the apex beam you can do that with. So just say you had a width where you would need, say, 5 beams for argument's sake. The only beam that you can extend the range on is the middle beam, the one in the apex. If you've got a flat roof, the maximum coverage is 15 metres in total. That's 7.5 on either side of the beam. And you treat the beam as if it was a piece of paper. So you don't measure the beam and say, okay, yeah, we've got a beam, say it's 20 centimetres wide. You start from either side. You treat the middle of the beam as a piece of paper, and it's 7.5 metres either side of that.
Okay, to answer the question myself that's come in, they've asked, do you have any literature that can be downloaded? I'm assuming, Nigel, you're going to direct them to your website, which is www.ffeuk.com, correct? I assume any literature.
That's correct. I mean, we do have a technical email address, which is technical@ffeuk.com, and I'm quite happy to answer any questions that people have via that. Or, like I said, or if Mark wants to forward them to my own email address, I can do that as well. Because I appreciate if there's a lot of people wanting to answer questions, and we're constrained by time. It's hard to get around everyone.
Indeed, it is. So we shall fire away. And yes, I will send everybody an email later with a contact email address for FFE and how you can watch us again on demand along with your CPD certificate. Right, let's keep cracking if you don't mind. So Kevin Ford from Wolverhampton Homes has asked, what protocols are the detectors currently suitable for?
Right. The main one is Apollo, because FFE are part of the same group of companies as Apollo, so that's how they own quite a lot of. They own Advanced, for example, who make primarily fire panels. So Apollo's the primary protocol we use, but we also do Zyton, Aritech, Cooper, Eaton. They're the main 5 protocols that we're looking at the moment. And that's mainly on the older range of beams. The beam that the 5000R has replaced has about 5 or 6 different protocols that it will run on. If you want to use a FireRay1, for example, on an addressable loop, we are working on addressable versions at the moment, but they're in sort of development. You'd have to use an interface module, switch monitor or something like that to interface between the beam and the bus. So it's bit of an open-ended question, that one. But yes, there are, but not not on some beams.
Okay, so another question that's come in from John Rogers at North Land Council. Does the beam detection integrate with a life safety fire alarm system rather than property protection?
Yes, they do, yeah. I mean, to be honest with you, the vast majority of beams are life protecting rather than property. So yes, I mean, it's basically they'll just go back to a fire panel, and then the fire panel will either contact the ARC or the fire services, whatever is deemed necessary. But yes, they are used in life and property protection.
Okay, so what type of surfaces can you mount these systems to? Right,
as a rough rule of thumb, if it holds the building up, then it's okay to use. So anything that's brick, metal, roof structures that are holding the building up, concrete, that sort of thing, it's okay to use. If you're using wood or plasterboard, or basically something that can move, the rough rule of thumb is if you press on it and it moves, so the room I'm in, it's got plasterboard wall at one end, brick at the other. If I press on the plasterboard, it moves. It's not a good surface for a beam to be installed in. Sometimes what I find is that, or adding in a building as well, especially in warehouses, because what I find a lot of times is that if an engineer can screw something to a wall that's easy, they'll take the easy route, but then they could have used, say, like an upright steel that they could have bolted the thing to, and then that would have been a much better installation. The trouble is, a lot of times you don't find that the building's flexing until 3 or 4 months down the line, and it may be that if the engineer is just doing the install, commissioning, and then walking away, you know, they've left the problems for other people to sort out. So yes, building movement is potentially a big issue with beams, but not if you install them properly. The other thing as well is that the longer the range of the beam, the more important it is to get a solid surface, because one of the tests I have to do, part of the many roles I do internal product audits, and one of the things is like misalign the beam. We've got this optical bench where we can offset the angle, and if you change an angle by 1 degree, the human eye can't really see that. I couldn't tell if something had been moved by 1 degree, but over 100 metres, that's nearly 2 metres of movement at the opposite end of the wall. So, sorry, at the opposite end of the building. So that gives you an idea of the further you go, the more important it is to have a solid surface.
Okay, so let's look at another question that's come in. I know you touched on this in the presentation, but I'd imagine the business submitted the question, missed that part of it. Does air movement affect beam detection system?
Yes, it does. I was going to say, normally, something like when we do training with people, it can normally be all day. So this is very, very condensed what we've been going through today. Yes, air movement will. If you've got extraction fans, for example, in a building, and they're sort of, you know, say a metre in diameter for argument's sake, and they're sucking air out the building, maybe because you've got dust or dirt that you're trying to sort of keep the levels of that down. If you had a fire, then the smoke would be drawn towards the extractor fan, and that's potentially going to draw it away from the beam. Conversely, if you've got an extractor in the roof and a beam is nearby, you may be drawing pollution through the beam, which isn't smoke. So just say you're sucking up dust into the roof area, then the beam might be adversely affected by that as well. So it is something to take into consideration, because a lot of times, and this is, I've been in this industry since '97, and I used to commission aspirators. It could be that you've got a perfectly installed building with beams, for argument's sake. They've never ever gone wrong. The engineer tests them every year, and they're all installed perfectly. But because of the extraction, it may be that if there was a real fire, the performance would be quite slow. So if you're worried about anything like that, it's always worth doing a smoke test just to see how the beam responds, and also maybe have cause and effects where if a call point is broken, then the first thing you do is you switch off the extractors. But it's something to definitely bear in mind. Same as stratification.
Okay, well, final question we'll go through for today before we round up. This actually comes in from the editor of Fire Safety Matters, Brian Sims. So using your industry crystal ball, what do you think will be the next major development for OBD? Without giving away any trade secrets, what might be the likely roadmap when it comes to research and development in this area?
Is this in beams?
Yeah.
Yeah. Okay. Well, if anyone went to Firex last year, you would have seen we had a little innovation room. It would be putting cameras in the beams. The reason for that is I think video detection is going to take over virtually every form of. It's going to affect beams, aspirating, flame detectors over the next few years. So one of the things we're doing is we're going to looking at the next generation of beams having cameras in them, so they will identify false alarms. So one of the biggest problems in our industry is false alarms. So if you've got a camera and it would work basically like a dash cam, you've got if there was an activation, then you can say, okay, look at the video. Yes, there was an obstruction causing the false alarm, or maybe there was some inrush of dust or dirt, or even maybe it was someone mucking about, putting their hand in front of the beam. So that's the sort of thing that I think we will go down. But in a wider scope, I think video detection is going to have a massive impact in our industry in the next 10 years. I know the fire industry is very conservative, so it takes a long time to change to new technologies. But yeah, video is going to be the way to go, I think.
I think you're 100% right, to be honest, Nigel, and you're right. It does take a while.
Anyway.
So far away. Nigel?
Sorry. Sorry. I finished what I was saying.
So anyway, that actually brings the last question for now to a close. Now, we have had other questions in. Now, if you haven't had a chance to submit your question, I'm going to be sending an email to everybody this afternoon, which, as I said, will include your CPD certificate, a chance to listen to this on demand again, and also a chance for you to register for our next webinar, which takes place next week on the 27th of May, which is to do with welding, one of the most dangerous jobs in the world. It'll all be about how to work safely during welding, and that's been delivered by 3M on the 27th of May. So I'll send you the link to that. But as I was saying, if you've got questions for FFE, obviously their website we mentioned earlier is www.ffeuk.com. But in the email I'm going to send you, we will have a direct email. You can ask any questions that I haven't asked. Do ask him again or submit new questions, and they will endeavour to get back to you as quickly as possible. We'll obviously do a write-up of this webinar on the Fire Safety Matters website, and you can see all the latest news in the fire and security sectors on there, which is www.fsmatters.com. And as I said, I will be giving you 1 hour of CPD given to you by our friends at the Institute of Fire Safety Managers. So really, all there is left to say is, Nigel, thank you for a brilliant presentation and for your time today. We really appreciate it.
Thank you very much, everyone.
Well, that was nice and succinct. Thank you to Tracy at FFE for all of her hard work on this, to Richard at StreamGo, our producer, to Brian, our editor, and most importantly, thank you to all of you for taking time out of your day. There was a huge number of you that took part today, and we're delighted that you enjoyed it. Take care, and nothing like last minute.
We got there.
We did. Right, here we go.